Chris Bachman. I'm the faculty advisor at Cal State LA for the Baja and Formula teams. I'm putting together a short video about doing some analysis of the forces inside CVT. If you haven't watched our quicker video on some of the fundamentals and how you tune and why the CVT is the way it is, go watch that first and come back to this one. This one will dive a little bit more into the details. So what I want to start off with is just kind of a diagram of the CVT where you can see the primary on the left, the secondary on the right, and being able to find some of the relative angles. So these thetas are the wrap angles, so the angle at which the belt is in contact with the pulley, and you can tell that you have these 180 degrees plus or minus this inverse sine term. So keep in mind when you go fully to shift out and the radius of the secondary on the right becomes smaller than the radius of the primary on the left, what will begin to happen is the wrap angle is getting smaller and smaller on the secondary until it goes less than 180 degrees, and as soon as it does that, these negatives will switch to positive. So just a little wrinkle to keep in mind that these equations change just slightly. The negatives will turn to positives for the top two equations on the wrap angle. So before I talked a little bit about how important the clamping forces are and how that clamping force is being turned into radial forces which will cause the belt either to be grabbed or it'll cause it to shift. So let's talk a little bit about how these clamping forces are generated. So let's start off with the primary pulley. So this primary pulley, I put together just a little schematic of it. So we have the black part of the pulley, which is all one inside pulley, which is all one piece, and then we have the white pulley, which is one piece with these flyweights on them that can spin out. Initially, these pulleys are pushed apart from each other and not engaging the belt, and the reason for that is this red spring is pushing from this black pulley and pushing the pulley on the bottom further away, keeping them apart. And as it will spin faster and faster, these flyweights will begin to want to move outwards. And as they move outwards, that'll overcome the force of the spring and clamp onto the belt. So we have the clamping force in this case. This is the force in the y direction. So we have the force of clamping. So that's how hard it's being clamped together. It's going to be equal to the force from the flyweights minus the force from the spring. And the force from the spring, it's just a linear spring, right? So the force of the spring, and this is for the primary, right? So this will be the spring stiffness K, right? Times you have some delta X for the install, plus some, we'll say, delta X from the shift. So you might have some pre-tension in there, and you should to keep it away. And so the spring, it's relatively easy to find. The flyweight's a little bit more complicated. So let's look at the flyweight. So a couple things that is going to be important is this flyweight's going to be rolling against a ramp. You might actually not have the actual flyweight roll. Maybe it's another piece, but the physics will turn out to be the same. So the ramp will have an angle. This angle can change throughout, so keep in mind for different positions, this angle delta could change. And the radius of the flyweight, so I'm showing the primary spinning about this axis, and the radius from this axis to where the flyweight's located, I'm going to call the radius of the flyweight. And then this angle of this link that's holding it, I'm going to use this variable psi. So what we need to do is we need to draw a free body diagram of the link and the flyweight all together. So, and to do that, we need to know what are the forces on it. So we have one force, which is, so we have the force from the ramp. So we'll call this force from the ramp, pushing it, and that has to act normal to the surface. And so it's going to have components. And so in the car axis, forward is X, and usually to the right as the driver's sitting is Y. So we'll do in that coordinate system. So we'll have force of the ramp in the X direction, and we'll have the force of the ramp in the Y direction. right? And this angle in here is also psi, just for reference. Okay, and then because this link has forces on just on the end, on the two ends of it, it's a two-force member. We're going to say it only has two forces on it as well. So I'm going to move this radius of the flyweight a little bit away. So we'll call this force on the link, and we'll do these two components. We'll do force of the link in the y direction, and then we'll do force of the link in the x direction, right? And this is still the radius of the flyweight. All right, so these are the forces on the system. So what we're going to do next is we're going to do sum of the forces. So sum of the forces in the x direction as we draw it are going to be equal to the mass times the acceleration in the x direction. So this is accelerating centripetally towards the center. So in this case, we're going to have the mass of the flyweight times v squared over r. So the v squared is going to be omega squared times the radius flyweight squared, and I could do p for the primary, right, divided by r. So we'll say the radius of the flyweight. So that'll cancel with one of these. So, and keep in mind that I'm just going to show this for one, but of course you could multiply this all by 3 or 4, depending on how many ramps and flyweights you might have. And then we have the stuff pushing it in the x direction. So we have the force of the ramp in the x direction, pushing it left, minus the force of the link in the x direction, pushing it to the right. Okay, and then we'll also have sum of the forces in the y direction. So the sum of the forces in the y direction, there's no acceleration vertically. So it could be moving, it could be closing or opening, but we're gonna ignore the accelerations in that direction because they're going to be relatively small. And we'll say that the force of the ramp in the y direction minus the force of the link in the y direction equals 0. So in this case, we'll simplify things for us so that we have the force of the ramp in the y direction equals the force of the link in the y direction. So those two are equal. And the thing that we really care about, this force on the link in the y direction, that's actually the force that's the equal and opposite force that's going to be causing the clamping force from the flyweight. So this is what we actually want in the end, the force from the flyweight, because that's this term right here, which is going to really give us our clamping force. So keep in mind, this is what we want to put everything in terms of. So what we need to do is we need to find a way to put this in terms of these two x terms. So luckily we know that both tangent of delta is equal to the force on the ramp in the y direction over the force the ramp in the x direction, and we also know that this angle psi, we know that tangent psi is going to be equal in the same way that this angle right in this corner, this psi, is going to be equal to the force on the link in the y direction over the force in the link in the x direction. So we can replace this term up here, and we know that the force on the link and the force on the ramp are the same, so let's just leave it as force of the link in the y direction. We'll substitute it later. So we'll have force, the link in the y direction, and one of these terms will have 1 over, the ramp term will have 1 over tangent delta minus 1 over tangent psi. And that's just because, like, for example, the force of the ramp in the x direction is equal to the force of the ramp in the y direction over tangent delta, right? And then I just substitute in the force on the link in that case. So knowing that what we want is FLY, which is force on the link in the y direction, which equals the force from the flyweights, that's going to equal to the mass of the flyweights times the radius of the flyweights times the angular speed of the primary squared. And this is going to be over 1 over tangent delta minus 1 over tangent psi. This is so sometimes you'll see inside here, sometimes people will include stuff like mass of the link, like maybe you think the mass has a significant weight times the radius of the center of the link, right? So this, it's not, you might just sort of have an addition term there. So this isn't completely true, because right now we assumed that this link and this flyweight were a two-force member, so that these forces act along. So the force from the link has to act along its length, where that's not entirely the case if you have some accelerations at the center. So it might be an okay way just to handle this small deviation from these values, but it's not strictly true. We also have another important thing that we're going to notice from here is that in order for this system to work, we actually need psi to be greater than delta. So this link needs to be sitting up higher than this ramp is. Otherwise it's not going to cause it to close. So a couple important parts right here. So if you put these all together, we can get the clamping force on the primary. And what you'll notice is, like, one important aspect of when does the pulley begin to engage the belt will be when this flyweight force begins to overcome this spring force. So we can put this whole thing together. So the force of clamping, right? So actually, I'm not going to rewrite everything. Force of the flyweight minus force of the spring. And this is all in the primary. So I could do like a sub P or something if I wanted to do it there. All right, so let's now start looking at the clamping force in the secondary. So the secondary, it'll have this inside pulley, and then this gray pulley is actually connected to the output shaft of the system. So this is actually what's driving everything. And what you can see here is you have, initially this is actually clamped together, and you have this red spring, and this red spring is actually pushing from the bottom of this kind of black top pulley on this gray pulley, pushing it up and together. And it also is turning this, and it's actually pushing in this direction as it turns, also clamping it together initially. So and that's what's holding it together. But what's going to eventually happen is the forces from the belt are going to push down inside of here hard enough to open this up. So that'll be one thing to keep in mind. And so I've talked also a lot about the secondary being sensitive to torque, and its clamping force being sensitive to the torque. Let's look at the system from a side view and look at some of the torques in this case, assuming it's not accelerating. So here's a view of the gray pulley. So this is the gray pulley. So it has a torque on it from the belt, making it go counterclockwise. So, and this could be the kind of the torque on the secondary. So you could do a tau S, and it's half, because half of it is going through this pulley, the other half's going through the other pulley. But it's also driving the output shaft forward with the full torque, and so kind of the equal but opposite reaction to that is this torque in this direction. So it actually, these two add together and you actually have clockwise torque on this gray pulley when you add those two terms together at least. Then you have two other terms. So you have this radius of the helix, which will be out to here. This is the radius of the helix. And so I'll draw it, I'm just gonna draw it up in my view. So you have the radius of the helix. And at this point, you have the force from the helix, which will be driving this in the counterclockwise direction. And you also have the spring. So this spring is going to be torquing this thing also in the clockwise direction. So this will be the torque from the spring. And the way you can think about that is it's torquing the black part in the black part counterclockwise. So it must be torquing the gray part clockwise in that case. So we have all of these torques in the system. And so we can begin to do a sum of the moments of the system, and we'll do this direction as being positive equals 0. And so we have the force of the helix times the radius of the helix minus the torque, and I can even say, let's just call this the torque on the secondary, so tau s, torque on the secondary over 2. So that's the torque being provided by the belt and what's going into your gearbox, minus the torque on the spring. Okay, so these two terms, can be relatively well understood because you know the torque from the engine potentially at your operating condition. You can know the gear ratio between the two belts because you know the radii of the belt on each of the pulleys, and the torque of the spring. So the torque of the spring is relatively easy to get. So the torque of the spring, it's going to also have, we'll assume it's a linear spring in this case, and it's going to have some lambda, some angle that it's installed at, plus some angle that it's shifted at. Right? So it has some angle that's installed. Did I use not before? Oh no, I didn't install. Yeah, so some angle that it's installed at, plus some angle that it's been twisted, that it's shifted at. And so if you know those, you can figure that out. Maybe one other drawing. So if I just kind of simplify, or I can do it on this one. So we know that this force on the helix is going to be in this direction, in this diagram. So this is the force on the helix actually in the x direction. But if we had the whole force on the helix, so force on the helix, and we broke it into components, force on the helix in the x direction and force on the helix in the y direction. So the force on the helix in the x direction. We know that there's a ramp angle. So the ramp angle is usually defined down here as, so if I zoom in a little bit, this angle will be eta. And so let's say that angle, I just like to think like, okay, if that angle is 90 degrees, then this angle is the one inside the triangle that's also going to be 90 degrees. It's not going to be the one above. So we can use this ramp angle to help us relate these two forces. Because in the end, we're thinking about, we want the clamping force. And so we know that the force of clamping in this case is going to be force of the helix in the y direction. In this case, this spring is helping with the clamping force plus the force of the spring And let's do secondary, right? So we have this spring is both adding some torsion and some compression. So it acts also as a linear spring in addition to this torsional spring. So this force of on the helix in the y direction is actually what we're looking for. So if we find that the force on the helix in the x direction is equal to the torque on the secondary over 2 plus torque from the spring, all divided by the radius of the helix. But we also know that the force on the helix in the x direction over the force on the helix in the y direction is tangent eta, which is the helix angle, which could be a constant or it could be changing as it shifts. And so we can find the force from the helix in the y direction, which is what we want, which is just going to be this tau. Well, let's start putting it all together actually. So we have this force of clamping. So the clamping force in this case is going to be, you're going to have both this torque on the secondary over 2 plus this torsion from the spring over the radius of the helix over tangent of this angle, right, plus the force of the spring from the secondary, which is, again, could be modeled as a linear spring. There might be some interaction between the angle that it's twisted and some of its stiffnesses, so you might want to be able to take that into account. But as maybe a first approximation, you might just give it a linear spring. So we'll say Ks, and this will be, again, we'll have some delta X. If it's initial install, plus delta X from the shift, right? So in this case, this is a little bit different. So in the case of the primary, right, as it shifts, the spring force is increasing. So as it shifts, this is going up, and so overall this clamp force is going down. In this case, the force on the spring in this case is going to be compressing. So this is going to be getting larger and larger. This is getting larger and larger, but this is getting smaller, a lot smaller as it shifts. So the clamping force, you want it to go down on the secondary. So that's a little bit about finding some of the clamping forces in the system. The other important part is being able to turn these clamping forces into radial forces. So radial forces from clamping forces. Right, so typically we'll have these belts, and they'll sit inside these two sheaves. That there'll be some force of clamping that's pushing this to the left, and so some force from clamping. Right, so this is getting pushed to the left, and that's getting pushed against this belt. This angle down in here might be some phi, some groove angle. And what's reacting against that is the force on the belt. So if we zoom in here, zoom a little bit in, a little bit here. So this force is being transferred. One way to think about it is this force is being transferred onto the belt, and you'll have some equal and opposite force. But let's draw the force on the belt, right? And this is gonna be the force on the belt, and it's gonna have a component that's radial, and it's gonna have this clamping force clamping. So I'm drawing this in the I'm drawing these forces on the belt, but obviously there'd be an equal and opposite reaction onto the pulley, and that's what's fighting this clamping force in the end. And you have this happening on both sides. So you have F clamp, you have F radial. Right? And so this whole thing is in equilibrium in this way. So if you have, and you only need the clamping force on one side because it's going to squish this, it's going to actually squish this whole thing together. And so you're going to have this clamping force, on both sides. So you imagine if you had like a block, right? And you had a piece of metal and you put a force on, force from me, I'll say here. If you do a free body diagram on the block, right, it's going to have the force of me on both sides, even just if you're pushing on one side. So that's what's kind of going on in this case. You're just pushing on one side, but that's actually causing forces on both sides. And this angle down in here is going to be this phi over 2 angle right here. So that's basically because it's from this triangle right here. And so we can say that the radial force is going to be, because you know that the total radial force, so maybe we'll say this is F radial over 2 and F radial over 2. So because those two will add together, and we know that F radial over 2 over the clamping force is equal to tangent phi over 2. So that tells us that the radial force is equal to 2 times the clamping force times tangent of the groove angle over 2. So I should probably box. This is the other key equation. And I think I boxed this one up here, but you might put it in with the other one. So that's how you go from radial to clamping forces. So let's talk a little bit about the radial forces, and really some things we need to think about is how much radial force do we need in order to grab the belt, and then we need to think about how do these radial forces cause the belt pressure, and so how does that cause the belt to shift. So let's just talk about how do you have enough to grab the belt. So for example, this is important on the primary. Initially it's just going to be rubbing against it until it can grab it in that low ratio, and then the engine speed will increase all the way to where it starts to shift out. And it's also important to design, it's an important design on the secondary, because that on the secondary, you're really trying to design just to stay 10 to 30% above the clamping force that you need throughout the shift, because that'll continue to change. So I'm going to call this part required clamping force to transfer torque. So to do this, I think a lot of the design starts with getting the clamping force right on the secondary. So I'm going to draw a picture of this is the belt on the secondary, and this belt on the top side has tension. So I'm going to call this tension on the taut side, and then on this side we'll have tension on the slack side pulling it left, and then we're going to have the radial force from the clamping on the secondary. Of course, you could do this exact same thing on the primary, right? I'm just doing the secondary as an example. So you have the radial force, right? And I'm going to use prime. So F prime is for forces per wrap angle. Right, so that's the radial force per the wrap angle. And this wrap angle looks like this, should be symmetric. So this is theta on the secondary, for example. And then I'll just use another color. We'll have this centrifugal force from the belt. So this is F prime centrifugal. Okay. So let's make an X direction, and let's assume that this piece of belt is not accelerating, so we'll have some of the forces in the x direction. We're counting the centripetal acceleration by using a fictitious force and changing its direction. So we'll say some of the forces in the x of this hole is 0. So we're going to have F, the radial component in the x direction. Oops, I should be careful with my signs. So we'll say just T taut in the x direction plus T slack in the x direction minus the force radial in the x direction minus the force centrifugal in the x direction. And so we need these total forces to be able to, and we need to get them in the x direction in order to do this. So to get these, we can call this angle right here, this is going to be theta of the secondary minus 90 degrees, sorry, 180 degrees over 2. So that's pretty easy to get. So if we say that, force radial in the x direction plus force centrifugal in the x direction equals the taut side tension in the x direction plus the slack side in the x direction, we can say this is just the taut side tension plus the slack side tension times cosine of theta secondary minus pi, the wrap angle on the secondary, over 2. So getting the x direction in there is not too bad. And typically we think a lot more about torques in the system since we know what's coming off of the engine. So let's replace it. Tensions with torques. All right, so this, we'll say this is the radius on the secondary right now. So we know for the belt not to slip, we can use Euler's formula that torque on the taut side over torque on the slack side has to equal to the exponent, the effective coefficient times the wrap angle. So this effective coefficient in Euler's formula depends on kind of the nominal, the traditional coefficient of friction over sine of half the groove angle, right? And so we've talked about the groove angle before. So how do we replace? And so if we know that the relationship between the taut side tension and the slack side tension, so if we know one, we can find the other. We can also relate both of these to the torque on the secondary. So the torque on the secondary is going to be equal to the taut side tension minus the slack side tension times the radius of the secondary. And we can just replace the taut side with the slack side. The slack side times e to the effective coefficient of friction times the wrap angle minus the slack side tension times the radius on the secondary. And so we can then just pull out this slack side tension E effective minus 1, right? And so, but what we actually want is we want the taut and the slack added together. So if we try and figure out what that is related to the torque, we can do the same thing and replace for the slack side. So we have slack side times this exponent of the effective coefficient of friction times the wrap angle plus the slack side. And so this is just, again, T slack times this exponential term plus 1. And now we can just plug in for the torque on the slack side using the tau, because we know this is the torque on the secondary. So we can just divide this term across and put it below here and replace it. So we know that this term that we're looking for is actually going to be the torque on the secondary. So the straight T's are tensions, right? And the tau is torque times what we're going to have is the exponent term plus 1 on top over, we're going to have the radius of the secondary times the minus 1 on the bottom. Right? And so this is the right hand, this portion of the term up here. So we'll put everything together here in a second. So this is the right hand side. So let's look for the centrifugal, and let's look for we have the centrifugal force, and then we can relate it to the radial force, which we know we can relate to clamping force. So centrifugal force. So the centrifugal force on a per wrap angle basis, since we know that's what we want, is going to be the total mass of the belt on the pulley times velocity of the belt over the radius of the secondary, so v squared over r, divided by the wrap angle on the secondary. Okay, so this mass of the belt on the pulley, call it mbop. So we know that it's going to be the total mass of the belt, so this is total mass over the length of the belt, and it's going to be times the length at which it's in contact with the belt on the pulley. So you have this term right here, and so we'll just plug that. And we also know that the velocity is going to be equal to omega r. So, and you could, do this all for the secondary if you want. So this centrifugal force on a per wrap angle basis is going to be mass of the belt over the length of the belt, so like a weight per length. So we're going to see that these two terms in the, well, let's just do it all. Theta secondary, radius secondary, and we'll have this on the top and bottom. So the bottom term is up here, the top term comes from up here. So these are just going to all cancel with each other. And what we're going to have is omega of the secondary squared, radius of the secondary squared. So mass of the belt over length of the belt times omega of the secondary squared, radius of the secondary squared. Cool. So, and how do we get the x component of these distributed forces? So x component from distributed. So if we have this belt, we can actually just divide it. We have the top and bottom, but we can just look at the top because we know when the half's going to come from the top and half's going to come from the bottom. We know that this angle here is going to be half the wrap angle then. And if we look at some F prime force here, and this is going to be up, let's say some angle beta. This angle in here is beta. And so the x component of it, which we want, is going to be cosine of beta times f prime. So putting this together, I know that the total force in the x direction from this distributed force around the outside is I need to integrate, I'm going to say 2 times, and I'm going to integrate the top half from 0 to half the wrap angle times the per wrap angle force times cosine beta d beta. So the integral of cosine is just sine, and sine of 0 is 0, so we're just going to get force in the x direction. It's going to be equal to 2 times the per wrap angle force times sine of half the wrap angle. So this will be, so the units of this will be in pounds force, or maybe pounds force. Let's just say in force. So this has units of force, right? And so, and the f prime has units F prime has, so the units of F prime, right, are going to be force per radians. So just a little note there. So it's putting this all together. So this is the force needed in order to get that torque. We have, so we go back up. We have both the radial force and the centrifugal force in the x direction. We knew this was the centrifugal force. We knew the radial force from the clamping force. So the radial force from the clamping force would be 2, and you need to put it on a per wrap angle basis. F prime clamp times tangent. I'm just gonna, I'll make it general now. So phi over 2, right? And because we gave it on a per wrap angle basis, we integrated it sine of the wrap angle over 2, right? So keeping the difference, the theta is the wrap angle, the phi is the groove angle, plus we have the total mass of the belt over the length of the belt times the speed times the radius squared of where the belt is at. And this is going to be equal to the torque on the specific pulley times 1 plus this exponential term times cosine theta minus pi over 2. This is a minus over the radius times exponent minus 1. Right, so here you can see this will help you find the clamping force that you will need in order to deliver this torque. And I assume you can massage this equation around to fit your needs. The last aspect of this that might be important, so that's important because you want to set the clamping force in your system with your secondary, and you want to clamp it over just what you need in the secondary. But it also becomes important when if you want to see when can you, what RPM are you actually going to be able to grab onto the belt, right? Because the clamping force of in the primary, because the clamping force in the primary is related to how fast it spins.
So this relationship can also be used to predict the shift profile of your CVT. So one way to think about this is that you have this belt. It's getting pushed out by the clamping forces in both directions. And it has its centrifugal force in both directions. And then the tensions are pulling it together between internally too. So and the reason I look at those is if we take a cut down the middle, that's basically the equilibrium we just did. And so how we predict whether it's going to shift or not is if whether at equilibrium these forces are all going to be equal in terms of the two tensions will be equal. So as a result, these forces will be equal to these forces pushing the system out. And so let's analyze the shift points along equilibrium. And so we can look, and to do that, we'll look at, this is the radial forces from clamping. and centripetal acceleration. So, and we can compare these on both sides. So if we look at this term, 2 sine theta of the wrap angle over 2 times the clamping force on a per wrap angle basis times tangent of the groove angle over 2 plus this centripetal acceleration term, which we kind of look at as a centrifugal force. Right? And what you'll actually find is this half angle wrap angle, because any additional wrap angle, so if they're the same size, you're going to have 180 degrees on both sides. And as you deviate from that, you're going to have angle added. You'll have 180 plus the delta on the wrap angle over here, so the theta of the secondary, and your theta of the primary equal to 180 minus the delta. So any gain or loss, it's going to be the same on both sides. And what you find is when you divide this by 2, this is going to, in terms of the unit circle, in terms of sine, one's just going to be on this side and the other one will be on this side. So it doesn't actually change this term, so this term doesn't affect it. This term is actually the velocity squared of the belt. So in this analysis, this will actually cancel. It'll be the same for both the left and the right. And so what you're really comparing, and then the 2 doesn't matter. So what you're really comparing is you have the primary side, you have the secondary side, and you're really comparing the clamping force on a per radian basis times the groove angle, tangent of the groove angle, and we can say P for primary and F clamp force of the secondary. So we're going to put a P there for primary, secondary over 2, right? And so if you're slowly shifting, and so you're not having large accelerations, these two will be equal along the shift points. And so that's a useful relationship, because you can plug in, you can talked about above how you get these clamping forces for the primary and the secondary, right? So we've talked about that all up in here about how do you get these clamping forces, and you can put them on a per wrap angle basis under your different scenarios. And so the order of doing this, so we're going to look at 2 graphs again. So we're going to look at the RPM of the engine versus the vehicle velocity, and we're also going to look at the torque on the secondary. So I should use tau of the secondary, torque of the secondary, versus the velocity of the car. We can look at both of these. We know this one, it starts out traction limited, and then you become propulsion limited by the power of the engine. So the first thing you want to do in this design is you want to ensure that you have enough clamping force to transmit the torque on the secondary, but you don't want too much. So what you don't want to do in red is have some flat. And so, because that's going to wear out your belt, and what it's also going to do is it's going to cause inefficiencies in the system. So the CVTs that the secondaries on most of CVTs teams are using, they're torque sensitive, as I showed above. And so you can get something, something maybe closer to this. And so you want to stay, so this is what I'm trying to draw here is the torque that can be transmitted. So the clamping force. rule of thumb I've seen in some of the handbooks is 10 to 30% above what you need, but no point of going over that. So first you design your ramp angles and of your helix and your secondary and the torsional spring so that you achieve this. Then you can begin to think about this desired shift profile, which here's maybe your low gear, which has a high gear ratio. And here's maybe your high gear, which has a numerically low gear ratio. And so you get that right first. So this is kind of step one. Step two is you want to get this shift out point where it starts the shift around your peak power RPM. So PP for peak power. So this is item two. So, and you do this, you can do this with the design of your flyweights as well as the ramp angle the initial ramp angle that your flyweights sit on. And then I'd say the third thing you want to get right is you want to make sure you don't want this to travel up or travel low. You want it to sit right along as close as possible to stay along this peak power point. So 3 is to get that to stay along there. And so you can do that by changing the shape of the ramp as the flyweights will travel along it. You can also change the stiffness of the spring in the primary. Another thing after that, which you might begin to think about is you might think about, okay, where's the engagement? So this is where the flyweights overcome, and this might engage a little more in here than that, but the engagement point, and that's when the flyweight forces overcome the pretension in the primary spring. And so that you can use shims to set the pretension in the primary spring. So this, you might set this kind of engagement, somewhere around big torque or, several hundred RPM lower than your peak power point. So this might be step 4. So I think that'll get you in the ballpark. The other thing to think about is, so this is assuming that, things are changing slowly. There's not big accelerations. The clamping forces are in equilibrium, but there could be some accelerations. And you see that with the overshoot here. And so keep in mind, if this term on the left is bigger, that means the clamping force is bigger on the primary. You're going to have, shift out. You're going to be shifting. If your secondary forces are bigger, you're going to have some back shift. Right. So there are dynamic aspects that we haven't included here. It's more than I know about. So if you're doing a lot on that, we'd love to discuss it, of course. Kind of general rule of thumb is like more aggressive helix ramps. So like lower angle ramps will make the secondary more sensitive to torque, and so that'll make the dynamics faster. So I've heard that before, but I don't have any data on that, and so I hope this gets everyone going on thinking about their CVT. And this is something we're new about thinking about and testing. So if you have some data and would want to talk about it, feel free to reach out, and good luck.